We're welcome to a mechatronics video on Quadrature Encoder and using an encoder on a motor. This demo is going to show just a standard brush DC motor with an encoder. We will step through, hook that up, and then we'll write some basic code in our ATMega to do quadrature encoding to keep track of the position with quadrature or four times the number of pulse count resolution, keeping direction forward and reverse. We'll work our way up. So we're going to make little baby steps and work our way up from there. Let's first take a look at our hardware. Here's our hardware. Great to see very nicely. So I've got two power supplies because they're just single output power supplies. One's going to run the motor, one will run the encoder. We've got an oscilloscope so we can look at signals coming out of our encoder. And here's our little system. I've got a brush DC motor in the back. You can see it's brushed. It's a DC motor, brush because it's got two leads. It's got an encoder at the top, but I'm not using that. We flip underneath. A nice little timing belt drive system runs over this little tensioner to a pulley that runs the big disc up on top. Have a nice little constructed thing. This pulley is suspended directly off the motor, so the bearings in the motor are supporting this pulley. This pulley down here is supported, the shaft supported in bearings contained in this shaft. Actually kind of a nice little setup. And then on the upper end of this shaft, right up here, you can see I've got my encoder. And this is one of the US digital encoders. We saw several of these. This one actually has a pass-through shaft, so it allows this shaft to pass right through it. More typically, they have a hub that goes on the end of the shaft. This one's kind of nice. It passes through, gets it out of the way, so it's not, the encoder is not sticking out of the way in the bottom of the top. It's right in the middle, kind of nicely protected. Off the back of the encoder, these four leads. There's an orange and a brown, which is my power and ground, and then a yellow and a blue. Those are my two channels A and B. So this encoder happens to have four. When I grabbed this out of the lab, it looks like there was a H bridge attached to it. We're going to ignore that. We're just going to run the motor directly off our power supply. So for this purpose, we're just going to be tracking that encoder. So first things first, let's connect our motor. So I've got the two leads from the motor here. I'll take this upper power supply, let that drive my motor. So I've got my leads. And I'm going to connect them across the motor. I'll do this over here. Not off the screen, but I'm just connecting it to the motor where it would go into that driver or where the leads end. Alligator clip. Okay, now it's connected. I'll turn my power supply on. You should be able to catch that just in the corner of your screen. It says output off. I've turned the output on. And I'll start bringing up the voltage. You can see there I'm at 2 volts. And I've got a slow speed. I could go down to 1 volt. Very slow speed. Doesn't take much to stop it. Oh, there was about a 3-to-1 reduction off the motor. So the disc is traveling at about 1/3 the speed, but 3 times the torque. There's 3 volts, 4 volts, 5 volts. We know that speed should be generally proportional to the voltage. So I'm controlling the two there. Okay, so I'm going to leave it right at a middle speed. Next, let's connect our encoder. So we need to bring 5 volts to the encoder. So I'm going to jump to the power supply below. I just turned it on. I'll take the 2 leads. Bring up this power supply here. And I'm going to connect them to the screen. Wait, enough room. I'm going to connect them to the leads, in this case, the orange, which is there, and then the brown. So that's going to be my 5 volts in ground. So I'm connecting them. You can't see me, I'm off the screen, but I'm connecting those two. So you can see it running around. And then I'm going to go over here. I'll turn my output on. Since I'm running this this IC device, it'd be nice to have my current limiter. I'll just carefully watch my current to make sure it doesn't go high. I'm expecting a small load, somewhere to 5 volts. I'm seeing 22 milliamps. That's a nice low load. That seems very reasonable. 22 milliamps seems reasonable to drive this little encoder. So that seems good. So I'll let that go. And then finally, let's look and see if we're getting signals because I'm driving the motor. So I'll turn on my oscilloscope. I've got, it's a 2-channel oscilloscope. I'll take the first channel. I'm going to call that channel 1. I'm going to connect it to the first output channel on my encoder here. That will be our, I'll call channel A our blue lead, and I'll call channel B our yellow lead. So I'm going to connect channel A to channel 1. I guess I could just call them both channel A. At the moment, it's a little bit of a noisy signal. I don't have my ground connected yet. Got that connected so I can see I'm getting nice, clean, square pulses here on channel 1. Go ahead and connect channel 2. So I guess from here on out, I'll call channel B on the encoder. So I'm connecting here to channel B, which is the yellow line. And I think the grounds, I think it already kind of grounded internally. So the former ground. So it's very happy there. So I'm getting this output. Notice we talked about this. It's the it's out of phase by 90 degrees. So my 2 square waves are not aligned. They're out of phase by 90 degrees. The beauty is if I look at channel A on top on a rising edge, I can see that channel B is low. Okay. I can see that. If I were to change the direction, I'm going to change the direction by changing the voltage at the input of the motor. That'll change my direction. Now it's going the other way in case you were watching the disc. Now on a rising edge of channel A, my channel B is high. Okay, so rising edge of channel A, channel B is high. Here I'm rotating in a counterclockwise, or we'll call it a positive right-hand rule, thumb going up, positive direction. Let's flip that again. So we call it negative direction, a negative direction on a rising edge of A, B is low. So we can tell the direction here. Oh yeah, and by the way, this is going right-hand rule, negative direction. Okay, so we can tell both, well, we're seeing pulses coming in, and we can tell the direction by the phase. Is channel A leading B, which it is, or is channel A lagging B, which it wasn't in the direction. Let's observe another thing on our scope. I'm gonna first slow the I'm gonna slow the motor down a little bit. As I slow it down, look at the pulse width of these square waves coming in. Much slower. I can scan over a longer period of time. I can stop that so we can take a look at what's going on here. Move it around because I've freezed it. But the time between one pulse to the next, that tells me the speed of the motor, okay? So if I speed up the motor, the time between, and I need to, here, let me, so if I, and let me also center that back up, okay. So if I speed up the motor, the time between the pulses should shorten. I'm at 3 volts there, I'm at 4 volts, 5 volts, because these pulses are coming in faster, less time from one pulse to the next. So each pulse is a fixed slot on that disk of the encoder. If I slow down, the time between them gets much longer, right to the point where I'm marginally moving. Let's zoom out a little bit. Yeah, and actually you can see pretty big variations because the voltage is so low, the little bit of friction in the belt is just making it hard to overcome. So it's actually speeding up and slowing down very significantly. I would need some kind of good controller to maintain an accurate speed here. And it actually takes almost nothing for me to stop it. Very low voltage, very low current going to this motor. Let me bring it back up. Okay. So we can see everything working just like we expect here. Back out a little bit. Now we're ready to see if we can start counting pulses. So let's, I'm going to move this image over here, kind of out of the background. I'm going to use my ATMega. So Here I've started I'm using the Arduino IDE, so I've started a base, just a default program. We'll jump to our notes. To capture encoder counts, we're going to use the input capture, one of the input interrupts, an external interrupt. I'm using a lot of different names. We're going to use some of the external interrupts on the ATMega. I'm going to scroll back up to the beginning of these notes where we talked about these. You can see we've marked them all up. And here was a little table we created that talks about the external interrupts that we had available. We had 8 of these fully featured external interrupts, int 0 through int 7. And then we had another 24 less featured, but still quite a few of them, pin change interrupts, PC int. So you have PC int 0 through 7, 8 through 15, and then 16 to 23. And this little table showed us where everything was connected. Lots of marks on here. Okay, so for this operation, I've got 2 channels, so it makes sense that I would use 2 interrupts. I'd like to capture in rising, maybe falling edges on each one at some point independently, maybe even measure the time. So I want pretty full featured interrupts. So I'm going to use these external interrupts, these 8, and I'm going to look across which ones could I choose. I'm going to choose int 4 and int 5. They are located on PE 4 and 5, and I actually have the Arduino board breakout, that EVB or evaluation board breakout here, and it's saying they're on pins 2 and 3. So we'll go ahead and use int 4 and 5. What we're going to do is let's take a little screen grab of this. Go down here, start new stuff. So we're going to connect channel A to int 4, which is also PE4 or pin 2 on the Arduino EVB. And channel B from our encoder will go to int 5, which is PE5. And I'm going to walk over here for just a moment. I'll pull up the video or the camera so you can watch it. Here I've got my ATMega on the Arduino Mega evaluation board. I've got this red lead connected to PE4, the blue lead connected to PE5. So I'm going to reach right in and connect these 2. Let's make sure I get the order correctly the way we talked about. Yeah. I've connected PE4. I've connected PE5. Okay. So now my ATMega is connected. I also have it powered through the USB cable, so I can get started. So let's jump over to our code. So we'll start off with a program name. We're going to call this Quadrature Encoder with ATMega. So we're going to track position, maybe velocity at some point of our motor using an encoder, an incremental encoder. It's got 2 channels. We're taking channel A is going to int 4, which is also PE4, and channel B is going to int 5, which is also PE5. Okay. We may come back up and add some more notes as we move along. In setup, oops. Okay, so now the first thing I need to do, I'm going to jump to setup, and I need to define my registers. First, I notice I'm using port E, so I've got to set the data direction register of E, and I'm going to set it all to inputs. So those are zeros, 1, 2, 3, 4, 5, 6, 7, 8. So I'm setting all of port E to inputs. Okay, next thing I'm going to do is set up my interrupts, or my external interrupts. Let's call that the external interrupt registers. These are all connected to timers, so I kind of throw that word in. Timer interrupts, but I think external interrupts is the right word to use right now. So the first one I'm going to define is the external interrupt control register A. If I look at our notes, let's go look at that register and see what we're supposed to do for that register. Jumping right up here, it is external interrupt control register A that controls the sense control bits for the interrupts. It looks like interrupts 3, 2, 1, and 0. Well, I'm not using those interrupts, so I'm just going to make this guy be 0. So this is not needed since we are using int 4 and int 5. Okay, next I have the external interrupt control register B, and that one is used. It's right here. And I've got the input sense control bits for 7, 6, 5, and 4. Okay. And down here, this table shows me what I need. If they're both zeros, low level generates interrupt. 0, 1 is any rising edge. 1, 0 is falling edge. 1, 1 is rising edge. Let's use the rising edge to start with. So we're going to start by triggering rising edges, which means I need 1, 1 for the sense control bits. So it looks like I've already marked ones here, but I'll set those bits high for the sense control bits. So if I start at the left, sense control bits for 7, I don't care about them being 0. Sense control bits for 6, leave them 0. Sense control bits for 5, they're 1, 1. So I'm going to trigger on rising edges. 4 is 1, 1. So I'm going to set sense control bits to capture on rising edges of int 4 and int 5. Okay, next I have the, let's scroll down. The next register I have is this external interrupt mask register. And this is just the mask needed for each of those, enabling the interrupts for each of the, or excuse me, yeah, enabling the interrupt service routine for each of these interrupts. I'm going to leave it off for 7, off for 6, on for 5, on for 4, off for 3, 2, 1, and 0. So I'm going to enable interrupts on int 4 and int 5. And next I have the external interrupt flag register. And this, I'm in this case, these bits get set when I get an interrupt. I'm going to actually clear them. You clear them by writing a 1. So as soon as I enable it, I'm going to clear it right off the bat to make sure everything's kind of nice and cleared. So I'm going to go 0, 0, 1, 1 on 5 and 4 to clear those. So I clear them by writing a 1 to it. I know it's a little counterintuitive, but I'm going to clear interrupt. I type flags on int 4 and int 5. Okay. So there I've got, it looks like I've got my register set. I am going to, in this case, I'm going to show my results on the screen. So I'm going to start the serial monitor. I'm going to print to the serial monitor. So I'll do serial begin, set the default baud rate. And so this is so I can print results to serial monitor. A little software program that runs in the background. Okay. Now in my main loop, really all I want to do is tell my current position. So my current position is going to be, so I'll just print it out. So serial dot print, I'll print a new line every time. And I've got to show my position. I'm going to show, let's start by showing it in terms of encoder counts. So I'll make a variable called encoder counts, print that to the screen, and then I'll do just a little delay. I'm going to use Arduino's millisecond delay kind of handily. So there's a ½ second between counts. And then that's going to be it for my, well, that's kind of it for my program. Now, a few issues here. First of all, what's that encoder counts? I didn't declare that variable. That's a variable that I want to keep track of inside the interrupts. So the way I have access to variables inside interrupts is by declaring them as global variables. So I've got to assign my global variables. I'm going to use these in my interrupt service routines. So the first one is that encoder. So let's make our first variable be an int encoder counts, and I'm going to initialize it to 0. And yeah, I should be good. Now, the remaining element is to create the interrupt service routine, do that, the thing that's actually going to do the work. Every time a rising edge, if I grab this and come over, every time a rising edge comes by here, you know, that one and that one and that one in time, I want to trigger and then index my encoder counts. So I needed to create my interrupt service routine. If we look at the notes, we are reminded that we had the interrupt service routine here, the jump vectors for those interrupt service routines. Here's int 4 and 5. The jump vectors are at the earliest RAM locations. The Arduino IDE has a header already mapping those. So since that's the IDE we're using, we're going to use it. I have the jump vector table here at the bottom of our notes. And here they are. So the external interrupt request 4, the jump vector is int4 underscore vect. So I come over here to my code and I'm going to declare that make this guy. So I'm going to make my ISR for int4, and it's going to be ISR parenthesis that interrupt vector name, which has already been created. So it's int4 underscore vect. So when an interrupt occurs, it gets redirected. It sets a flag. And since we've enabled the interrupt, well, I guess maybe the flag is because it's enabled, but it also spawns this interrupt service routine. You always need, by the way, you need to have this guy because this also clears the flag. You need to have it even if it's empty. In our case, it's not going to be empty though. Every time a rising edge comes in, this gets called. What are we going to do? Well, we're going to increase our encoder counts. So we'll let encoder counts equal encoder counts plus 1. There. Now we've got some working code and we can go ahead and give this a try. Let's call this Quadrature Encoder. It's compiling. Oops. And it doesn't like my spelling. Let's try it again. Okay. Compiled. It's uploading. I'll go ahead and open the serial monitor. Now we've already connected everything. So here's my serial monitor and I'm getting, don't you know it, I'm getting gobbledygook. So let's just pause this for a second while I decode things. I've got to track down why it's not liking. Oh, actually know the problem. I made a little mistake. I even mentioned it. So here, I need to actually, since I've enabled both interrupts, I need to, I actually said it and didn't do it. I need to turn on the interrupt service routine for both, even if I'm not doing anything. And I'll just make a blank See what this does. Okay, so let me do one more thing. Okay. Well, it's funny because I actually said what to do, but somehow failed to do it. I had didn't create the ISR5, but I was getting interrupts since I enabled it. I plugged both in. I was getting interrupts on both, and one interrupt was sending the program to memory that just wasn't mapped at all. So it's kind of really being pretty risque there with my code. Anyhow, over here you can see I'm getting counts. I'm counting my way up. I'm up to, at this point, 16,000. I mean, if you wanted, we could restart, but it's just going in one direction. It's counting upward. I'm at 20,000. I've used an int. I think int by default is assigned 16-bit integer. So I'd expect it. I started at 0, so it should count up to like 32,000. Roll over and come on down. So let's just watch that. I'll speed it up a little for fun. See, it's going faster. The counts are going up faster. And it rolled over, went to negative 32,000, and it's just continuing. Okay. Let's also, just for fun, observe what we have. So here's my serial monitor. Let me just do a couple things. Let me slow this back down, reset it. Okay, so I'm back to 0. So I'm just counting from 0. I just reset this guy. I'm counting from 0. You can see my count. If I slow it way down, the count will slow way down. So while I'm not tracking the speed, I mean, it's very visible. The rate at which the counts come in is very much a function of the speed. So if I were to measure the time from one encoder counting to the next, I could get a handle on speed. I haven't done that yet. I'm getting lots of counts. I mean, what's the resolution here? I guess it would be nice to turn the disk one full rotation. We could do that actually. Let's do that. I'm going to unplug, disconnect the motor. So now it's not moving at all. And so I've got a steady count. I'm going to line up this, I've got this pattern of holes. I'm lining it straight up with the motor. I'm going to reset my board. So kind of reset my count. And I'm going to do one full rotation. Very carefully. And that says 360. So I suspect I've got about a 360 counts per revolution, or one pulse each equals a degree. That's kind of handy. I might have chosen that encoder that way. Okay, so we can plug it back in. So that gives us just a measure. Actually, what we're measuring is counts, but also happens to be degrees. That's kind of nice. Now let's look at something here. I'm going to go in the opposite direction. Let's see what happens. Unplugged. Let's go in the opposite way. Still counts up. I'm not seeing a difference between rising edges or falling edges. So frankly, I'm counting in degrees, but I'm not getting direction. I'm not really getting speed. So that would be nice for a follow-on video. But this first video, you can see we're able to track our position in degrees of our encoder relatively accurately. We're only using one channel. We're just catching on this rising edge of this first channel. So we'll add more features as we move along. Thanks for joining in on this little recording. That you see my face. Thanks for joining on this recording, and we'll pick up another one soon. Thanks. Bye.